Thank you so much for watching the latest AI Weekly update on Henry AI Labs up to the week of August 7th, 2021. Hands down, the most exciting project this week is Open-Ended Learning Leads to Generally Capable Agents by DeepMind. This is reminiscent of the OpenAI paper that tried to solve the hide-and-seek agent and showed that this multi-agent learning leads to emergent tool use. As they are solving this hide-and-seek task, they eventually learn to push the objects around such that they form enclosures so that the hiders can hide from the seeking agents, and the seeking agents learn to build ramps to run up into the enclosure, and that's what happens in the OpenAI hide-and-seek paper. This paper from DeepMind is extending the scope of this kind of research. They have this Unity-generated environment that renders all these different topologies of objects. You can still push around things like these squares and the different shapes and sizes of them, and then create all these different games. So they have all these different games from this logic language where you have, say, two agents, and then they might have some kind of cooperative objective where they both need to, say, push this tile onto, say, like a blue square or something like that, or maybe it's hide and seek where this agent needs to see this agent, and then they also have like a little laser they can shoot at each other if it's, say, push this agent off of this cliff. So it's sort of like these like Mario Party games, if anyone listening remembers that, where you kind of have like these random games where you're sampling some task, and then it's pretty straightforward to figure out how to interact with the other agent. So there's this very diverse space, and that's this idea of open-ended learning, because you can render all these different environments, you can render all these different task objectives, and then you have all these different policies of the co-player that also create some variation in the environment. So another really interesting detail about this is the use of population-based training in the way that they structure this curriculum in these open-ended learning objectives. So if you remember a recent video on Henry AI Labs going into the multitask Minecraft reinforcement learning environment, they have this strategy of using the change in learning success in order to structure the curriculum and sample which tasks to present to the agent next. So here they have this thing they call normalized score percentiles, and they use this they have this set of dynamic hyperparameters that are optimized with population-based training in order to train these agents and have the right configuration of the curriculum, and then they'll do a policy distillation and then restart this population-based training strategy. So overall, a really interesting study making advances on this really exciting idea of open-ended learning. And as Jeff Clune and Kenneth Stanley described this as an algorithm that might be interesting if you let it run for 1,000,000 years, which is a really interesting idea. And these algorithms that explore these really diverse environments and lead to this interesting behavior. So next up, we have another intersection of reinforcement learning and curriculum learning. So the idea behind persistent reinforcement learning via sub-goal curricula is that instead of having to solve this problem where you reset a robotic agent back to its initial state, so say you have a robotic grasper and has to pick up an object and put it in a bin or something like that, it's hard to exactly reset it to the state of the original cube, the original configuration of the robot hand, and so on. So doing these manual resets is a big problem that they describe in the paper. So in order to solve this, they have these goal condition policies that try to just reset it to a state that's near the goal. So you try to go to this state, say state SN is the final goal state, and then SN minus 1 was the step that you took to get there. You try to learn a curriculum to just try to get to these intermediate states before having to go all the way to the goal state, and this avoids this problem of having to reset it all the way to the initial state to continue the learning with these robotic tasks. In the space of natural language processing, we'll start off with domain match pre-training tasks for dense retrieval. This paper is showing that this recent trend of scaling up the size of the models and the size of the data sets has worked well for most of these natural language processing applications, like say the glue benchmarks and question answering and these kinds of ideas, but it hasn't worked well for information retrieval. So as shown here, information retrieval is where you're trying to match a query with a passage, and this kind of idea for, say, you have a massive collection of passages or documents, and you're trying to match a query with this corpus of documents to return the most similar document or passage. So what they show in this paper is that if you scale up the size of the data using this 65 million probably asked questions data set, as well as this 220 million Reddit data set, that it is able to benefit from scale when you have the right data set to do so. This next paper isn't really particular to deep learning, titled Growing Knowledge Culturally Across Generations to Solve Novel Complex Tasks. So what they're doing is they have human participants, and they're trying to solve one of these games. I think it's like kind of similar to an Atari game, and they only get 2 attempts at the game, and they have to write a message for the next human player in the generation of trying to learn the game. So this is the idea of growing the knowledge culturally, is that you pass down some information about what you've learned about the game in order to finally have the next player is able to just read the description of the game and then figure out how to play from that. And then they have like how much they're paid is incentivized by how well these messages perform. An overall really interesting way of structuring this kind of task, and maybe this would be an interesting kind of framework for a deep learning project in the future. Next up, we have language grounding with 3D objects. This paper is motivated by the idea that if you're asking a robotic agent to grab you a coffee cup, you might describe it with physical properties like the cup with the wide handle, or the tall cup, these kinds of ideas. So this idea of language grounding is to rotate the cups and then use these different rotations in order to match a language description of the cup with the view of the cup. So it's trained with a contrastive objective where you'd have two different cups, and then you'd rotate them 360 degrees, and then using the clip encoder to encode the visual representation as well as the text description, and then you'll see which similarity score is higher between the two cups, having the ground truth label of, say, the yellow cup, or the like this kind of shape on the cup is how you're describing the two different cups. So an interesting idea of using language to kind of describe these rotations of the cups, and then use this to ground language to have more of a three-dimensional representation of the visual world. So rounding up the papers in natural language processing, we have a couple really interesting surveys that have come out this week as well. Pre-train, prompt, and predict, going over all the different details of these prompts, which are how we're prepending context to these language models in order to guide them to different downstream tasks without any kind of explicit fine-tuning, or in some papers like null prompts. If you do have fine-tuning with a prompt, you usually do, say, just have a minimal parameter change like these adapter layers, bit fit, and these kinds of ideas. So a really interesting survey coming through the different ideas in prompting. And then question answer dataset explosion, a taxonomy of NLP resources for question answering and reading comprehension. So this describes the, say in the T5 paper, the text-to-text transfer transformer, they showed how you could unify all these different tasks into the same kind of language modeling interface. And this is also showing how question answering datasets have kind of taken that similar unification, but then there's still differences between the data sets themselves. So they could be just turning classification into a question by saying, what is the sentiment of statement? And then you just mask and say positive or something like that. Template filling, when was mask born? This kind of closed task, this testing of, say, like the knowledge that's been retained in the model. And then these open-ended questions where you just ask it a very vague question and expect some kind of interesting generation answer to the question. So a very interesting coverage of these different question answering data sets, things like the different types of evidence, like Wikipedia, knowledge graphs, or just closed book question answering encoded solely in the parameters of the language model, and all these different ideas with respect to question answering. Next up, we have one of the most exciting successes of few-shot learning. Few-shot learning, again, is this idea where we're trying to learn a task from a few examples. So say we only have a few labeled examples, and we want to quickly generalize to learning new instances of this task. And this could be, say, learning a new class label. It could be transferred between the task entirely, or it could be a transfer between domains. This kind of way of thinking about how we structure these meta-training, meta-testing loops in this few-shot learning formulation. But particularly in this ProtoTransformer meta-learning approach to providing student feedback, they're looking at trying to use these rubrics to grade coding questions as the few example demonstrations. So they have these rubrics that correspond with different questions on tests, and then they're learning to bootstrap the rubric label for future student answer submissions. And they scale this up to the scale of 16,000 student answer evaluations, and then the students rate it as 4.6 out of 5 on the feedback that they're receiving from this model. So differently than just is it right or is it wrong, this model is giving feedback on exactly where the coding problem was wrong. Say you have these different kind of syntax errors that led to the error in the program. So they're using this prototype approach where to solve this few-shot learning problem, you learn an embedding for each of the different few-shot labels, and then you have this distance between the new inference embedding and then the class prototypes in this prototypical learning framework. They also add two more extensions to the prototypical representation learning framework, where they have this side information where they embed the question as well as the rubric choices into side information into the model, and they also construct additional self-supervised learning tasks for the representation learning. So overall, one of the most interesting applications of few-shot learning that I've seen yet, a really exciting paper on deploying this to real world, solving this problem of, say, these online courses and providing student feedback rather than just right or wrong with these answers. Next up, we have a humbling paper titled "Don't Sweep Your Learning Rate Under the Rug, a closer look at cross-modal transfer of pre-trained transformers." So previously there was a paper titled, I think it was "Pre-trained Transformers as Universal Computation Engines," or one of these kind of papers that are trying to show that you can take a pre-trained transformer trained on language modeling and then transfer that into, say, CFAR 10 or all these other tasks, and that in these previous papers you didn't even need to fine-tune the model, and actually fine-tuning it was shown to perform worse than just leaving it frozen. Well, this paper is showing that this is really the result of not looking at the learning rate, and this was the 10 to the minus 3 was the learning rate used in this paper that was saying that you could just take this frozen transformer and apply it to some new task. But if you actually look through the other learning rate values, you'll find that fine-tuning it does work better. So an interesting paper, kind of similar to, there was a paper that was something like a metric learning reality check that showed that these recent advances in metric learning weren't really being properly compared against one another. So interesting kind of grounding of this kind of finding. So next up we have the AAVAE, Augmentation Augmented Variational Autoencoders. So I didn't get too much into the detail of this paper, but from a high level overview, what happens is instead of having the global regularization on the latent space and how these latent vector Z's are distributed by having that KL divergence between the prior, which is a normal distribution usually, you're going to use the posterior on how you reconstruct augmented images to have a more local regularization. So you take the original image X and then you're going to put it through a data augmentation, encode that latent vector, and then you're going to decode that. And so you're trying to make the reconstruction loss with these latent vector Z's to be invariant to these augmentations compared to this global regularization of the prior. So again, I didn't get completely behind this details of exactly how this is working and exactly how it's different from, say, this variational lower bound thing and the elbow and all these ideas behind variational autoencoders. But generally, I think it's interesting to see these frameworks that are trying to integrate data augmentation into the autoencoder pipeline, because we've seen data augmentation power, say, contrastive learning, but it isn't really so heavily used in generative models like GANs or variational autoencoders. Also on this topic of self-supervised learning and the use of data augmentation, this paper titled Towards Domain-Agnostic Contrastive Learning is trying to form a way to use this data augmentation framework without relying on domain-specific transformations like how in images you use rotations, translations, brightness increases, horizontal flips, and these kinds of ideas, trying to create a contrastive learning framework that, say, would work for tabular data, graph data, any kind of data. So the augmentation that they use here is mix-up. So mix-up is where you say average the pixels of each location to form this mixed-up image, and then these would form the positive pairs, and another randomly sampled instance from the data would be the negative pair, and this would be the similarity distance, or you have that, say, normalized over a large sum of denominators, that kind of contrastive loss. So the idea behind mix-up compared to, say, they have a theoretical analysis comparing mix-up with, say, adding Gaussian noise to the instance A, and then how this helps learn the support of the distribution, these kinds of ideas. But generally, mix-up is a general data augmentation that can be used on any kind of data and facilitate contrastive learning for any domain. So next up, we have a really interesting success on dataset distillation with infinitely wide convolutional networks. So the high-level overview of dataset distillation is you take the original dataset and then you try to optimize it such that you have some optimized set of images or data set that performs the same on, say, the test set when the model's trained on this data set. So similar to papers like generative teaching networks or synthetic petri dish that might have this outer inner loop strategy of optimizing this training set, you're trying to optimize it for the performance on the held out real test set. And so what they do in this paper is they're exploring this idea of infinitely wide neural networks, which I really had no idea about before this week, but it's something about how if you scale up the width of the network, it converges into a Gaussian process, the way that the outputs of the neural network will be distributed as you increase the width, and some kind of optimization thing like that, some kind of thing to do with the kernel trick where you simulate going into higher dimensions without actually calculating it, this kind of idea, and something with this kernel ridge regression, which is how they actually optimize. And the details of this seem pretty interesting, but I didn't really get into it completely. But they are able to start off with these original images and then use this infinitely wide, I think, kernel ridge regression technique in order to optimize these images to distill the data set and compress it and then still achieve high test performance when training on these images only. Next up, we have a really exciting paper that is studying this idea of generalization, pointer value retrieval, a new benchmark for understanding the limits of neural network generalization. Previously on Henry AI Labs, I was really excited to present this paper titled Turning Tables, which is exploring how you can use Wikipedia tables to do this kind of symbolic computation, like, say, what an SQL query would do, where you aggregate and do sum, aggregate, list, these kind of operations. And those kind of symbolic operations on text is kind of what was described as a reasoning task. and described as reasoning skills within these neural networks. So this pointer value retrieval benchmark might be a better example of, say, a reasoning task. So what you have to do is you have to look at the top left part of the image in order to get the signal for how to read the rest of the image. So this 6 might tell you that the answer is in this bottom left corner. The 9 might tell you to look in the bottom right corner for the 3, and then so on. So the 3 tells you to look for the top right corner with the 0. So there are intervals like 0 to 2 means look in the top right, 3 to 6 say look in the bottom left, and then, or whatever it is. So this index of this top left is telling you which part of the image to look for the answer. And so they also have this as a sequence, so it's just a one-dimensional image string, and so on. These ideas of how you can have these inputs that are constructed such that you have to kind of have this multi-stage processing of looking for where to look for the signal and the answer to the image. So really interesting. They show that this does not generalize well. It doesn't pass this test very well unless you really scale up the size and enumerate all these possible configurations. And then as you increase the data, it does start to perform better, is what I think was the takeaway of the study. But overall, really interesting thing. It kind of reminds me of the, say, abstraction and reasoning corpus, the ARC challenge on Kaggle, and promoted from Francois Chalet. These ideas of forming these reasoning tasks over these images and thinking about the difference between reasoning and then I guess I'm not sure what the alternative is, but maybe just like intuition, quick generation of the answer. So next up is go wider instead of deeper. An interesting continued study on these mixture of experts layers, things like the switch transformer, these interesting ideas where you increase the width on these mixture of experts layers so that you have all these different feed-forward network layers, and you have this soft attention over which how you're going to route the input token embeddings to the different experts. And they're showing that they're able to achieve this performance gain over the original vision transformer by increasing the width of these mixture of experts layers. So not something that I know too much about, but I think it's just an interesting trend to see this kind of approach on, say, scaling out the width with these mixture of experts layers and the continued popularity of using this approach. And again, I think the switch transformer has something like 1.6 trillion parameters or something like that in one of these translation models by doing this kind of sparse scaling in the width. So an interesting idea and something that I definitely want to learn more about. So next up, we have a really interesting paper on geometric deep learning on molecular representations. And I am not an expert on molecular representations at all, but here's the high-level overview of or what I took away from this idea of geometric deep learning and how it applies to this. So geometric deep learning is where we encode geometric priors into our neural network architecture. So for example, the convolutional neural network, it has these 3x3, say, or whatever n by n parameter kernels that are slid across the image. They go left to right, top down, and so it's invariant to the translation of images. If you translate it to the left or the right, that kernel is still going to have roughly the same output. It might be slightly off put by the way that you've shifted the image and so on, but it's roughly invariant to these translation. So they describe the difference between, say, equivariance and invariance with these geometric priors with respect to how they change the output of the function and how this relates to molecular representation. So in this image, you see 5 different examples that, say, chemists have come up with to encode molecules. Again, I don't know anything about this, but the idea behind geometric deep learning is to have some kind of architectural prior that encodes the invariance to these different representations. So in this SMILES string, say there might be different ways of clustering the parentheses and so on, and describing the molecule that are really describing the same molecule. And this kind of thing holds for all these different ideas, whether it's a mesh representation or these other kinds of ideas, that you would have some kind of invariance in the geometry of the input representation space. And that's kind of what they're trying to get at with these graph neural networks and trying to encode this invariance into the architecture rather than something like, say, data augmentation, where you could just kind of like brute force this and permutate every kind of invariance that you know, and so on. These kind of ideas of geometric deep learning, definitely one of the most interesting ideas in deep learning. Then we have an interesting paper from DeepMind about learning from label noise, a realistic simulation framework for learning with label noise. So the idea here is, say, different from weakly supervised learning, where you have a bad label that comes from, say, web scale label bootstrapping. This is referring to, say, where you have crowdsourced annotation, and so the particular noise in the label can maybe be deconstructed by looking at some kind of featureization of the rater themselves. So the idea here is that you have 2 different parts of this. Firstly, you have a simulation of the label noise where you say train different model architectures with different number of epochs, hyperparameters. So you have a mobile net trained for 15 epochs or a ResNet trained with heavy data augmentation for 200 epochs. And you're using all these different models to label the data. And then you're trying to reverse the label noise by learning this thing they call a label quality model, where you use the features of the network that was used to label the data as an input to try to denoise the instance. So it's building on this framework of trying to learn with noisy labels, which is an interesting problem in these real world applications, and this idea of how you're actually building these massive supervised learning data sets and kind of the errors that will come out from that when you're, say, using crowdsourcing and these other kinds of ideas. So in this idea, you're using a label quality model to fit a parametric model that will take in some kind of featureization of the rater to try to decode the label noise. Next up, we have a really interesting idea on this problem of uncertainty estimation through the use of data augmentation. So we have these two different approaches of uncertainty where they're described as epistemic uncertainty and aleatoric uncertainty. And basically the idea is if the error is reducible or not, whether it's a problem with the model or a problem with the data generating process itself. So say you have this horse image that's been incorrectly labeled as a donkey. This is an irreducible error. You can't fit this to be a donkey because it's been mislabeled, compared to this image where even though it's out of distribution, it still is a horse image. So the idea behind this targeted augmentation approach in A Tale of Two Long Tales is to try to isolate these kind of reducible error images by applying data augmentation to get more views of the image, and then see if it starts to learn it, see if the instance itself is learnable compared to having a corrupted label as you use this data augmentation interface. So a really interesting approach on using data augmentation to distinguish between these two types of uncertainty, whereas they describe compared to, say, just assigning a single score for uncertainty or using the entropy of the output label distribution doesn't really tell you what the source of the uncertainty is, which is important for this kind of problem. To round up the AI Weekly Update, we have a really exciting demonstration of DALL-E Mini hosted on Hugging Face Spaces. And I think this trend of Streamlit and Hugging Face Spaces, and I think another one is called Gradio, this kind of idea of being able to host these deep learning models really cheaply and easily. Personally, I've used the Streamlit interface to just look at a language model and to have a little bit of an HTML template that you can kind of, have like a nice interface for visualizing your model rather than just using, say, a command line or a Google Colab notebook. You can easily create these kind of HTML templates for visualizing the outputs of these models. In this case, using the text to image generation, where you can input the text prompt and then see these generations from the DALL-E Mini model on Hugging Face Spaces. And I think overall this trend of facilitating creating these user interfaces for deep learning models is definitely something that is new and really exciting. Thank you so much for watching the latest AI Weekly Update from Henry AI Labs. There's a Notion page linked in the description of this video that contains links for everything that was covered in this video. Thank you so much for watching again, and please subscribe for more deep learning and AI videos.